Hi everybody, this is a walkthrough for an exercise on Euler cycles, and we're looking at these graphs and we want to know for which values of n greater than or equal to 4 do these graphs have an Euler cycle. Cool, so I think one thing that we'll keep in mind throughout this exercise is that for an Euler cycle to exist, the degree of each vertex must be even. So this will be something helpful for us as we go through these questions. So in part A, we're looking at k sub n. A is the complete graph with n vertices. So what does that look like? For example, K3, we have these three, and complete graph just means that each vertex is connected to each other vertices. So for K4, we'd have something like this. As you can see, each vertex is connected to every other vertex. So you'll notice that each vertex must have the same degree, and the degree of every vertex is just n minus 1 since we're connected to every other vertex. So in K3, for example, we're connected as a vertex to the other two vertices, so the degree of every node will be 2. So if we generalize, we would want odd values of n to get even degree. So odd values of n is our answer for this. Greater than 4, so starting at 5. In B, we have C sub n, which is cycle with n vertices. What does that look like? We just have, for example, for C5, this circular kind of structure, and it looks the same as we add vertices. So, cool. So you can see that no matter how many vertices we add, the degree of every node is still going to be 2, since every vertex is just connected to the vertices to the left and right, or adjacent to it, I guess, in kind of the cycle structure. So any value greater than n will get an Euler circuit. Just looks like this, just going around for any value. Cool. For C, we have W sub n, which is the wheel graph. And then we know that this has n plus 1 vertices. So for example, W4 would look like 4 outside vertices with 1 spoke vertex in the middle. So we can see that this is very similar to the cycle graph, except that every vertex on the outside edge is also connected to that vertex in the middle. So what this means is that no matter how many vertices we have, we can make it 5 as well. No matter how many vertices we have, the degree of every vertex on the outer edge will be 3, since it'll be connected to those two adjacent as well as the one in the middle. So no matter what value we have for n greater than or equal to 4, we won't have an Euler circuit be possible, since we'll have these odd degree vertices on the outside edge. So no values. Cool. And finally for D, we're looking at Q sub n. I'm not sure if we've gone over this graph archetype in class, but Q is the hypercube. So, for example, Q1 is a single vertex, Q2 is 2 vertices. If we haven't gone over this in class, then obviously just feel free to ignore it. But Q3 is this, and then Q4 is the cube-like structure. Cool. So, actually, I think this might be 0, 1, 2, 3. So you can see that with every increasing value of n, we duplicate the previous Q graph and then connect the corresponding kind of vertices to each other. So here we took this, duplicated it, and then connected the top and bottom, and then same here, the square we duplicated. So whatever the value of n here is, that's the degree of all our vertices because we're duplicating and connecting. So for example, in this case, when we duplicate this, we're connecting every vertex to one new vertex, which is its corresponding vertex in the copy. So that means for even values of n, the degree of every vertex will be n. So for even values, the degree will be even, and thus we'll have an Euler circuit. Again, if we haven't covered this in class, just ignore this part.